Grab a seat. Okay, so let me just recap where we are in this lecture series. It's me again. This is my last lecture. Glenn will be here soon, giving the last lecture. So let me recall these spaces of modular symbols. So remember the notation. V is just some module that has an action of some matrix algebras on the right. Gamma is some subgroup of SO2Z, and delta 0 is degree 0 divisors on P1 of Q. And something I should have done a long time ago, let me just give easier notation for that. So I don't have to keep writing that long thing. Let me call that sim. Like that's like for symbols. And that's the level gamma with values in V. Okay, so that's just the definition of what that notation means. I'll use that from now on. And let me just make one point. I mentioned before that these modular symbols are dual to other standard notions of modular symbols. There's also, these things map naturally to cohomology. Let me just write down that map. So there's a map to, it's just group cohomology here, with other interpretations. The first cohomology group with gamma acting on V, and the map is quite simple. If I take a modular symbol, then I want to make a cocycle cohomology class, so then I have to give you a map from gamma to V. So for each gamma in the group, I have to send that to something in V, and then I think it goes something just like that. I take phi and I apply it on, let's say, gamma infinity minus infinity. Wait, sorry. So gamma infinity minus infinity is degree 0 divisor, and then I plug it in. And if I didn't pick infinity, if I picked a different cusp, then I would just be changing it by a co-boundary. And so it's a well-defined map. And it's not surjective, but it's probably really close to being surjective, that map. Maybe just off by a little bit. And just some advertising other talks. I think in Samit's last talk, be constructing classes here rather than here, but close to the same thing using Eisenstein series instead. Period integrals of Eisenstein series. And then the modules V that we were looking at were these, well, these distribution modules. Let me first remind you there was an A. A was convergent power series on the closed disk. So this is where power series where the nth term is tending to 0, and here everything was defined over QP. And then D was the dual module. A into QP, this is continuous hum. And we had this nice concrete interpretation of this space just as sequences of bounded sequences in QP, because every distribution was determined by its values in all the monomials. And one can look at overconvergent modular symbols, and I stated for you this theorem of Glenn Stevens that I didn't recall. There's a map from, I should say, let me adorn it a little bit more. Let me put a K here and a K there. Remember, we defined a weight K action on this, and then there was a map from dk into sim K. A surjective map, and then let's just take overconvergent modular symbols and push them forward and get classical symbols. And so I called rho star sub K the induced map on modular symbols. So now I'm putting gamma 0 for gamma 0 of NP, and then I'm plugging in dk, and then that maps naturally to these classical modular symbols. This space is some big infinite dimensional space. This is some small, well, space we understand exactly by Eichler-Schmür. And then the theorem is that if I restrict to the subspace where UP acts with small slope, in this case less than K plus 1, then that map is an isomorphism. So this is the theorem that's going to occupy the lecture today, explaining why this is true. And just to point out, I also talked a little bit at the end of the last talk, this is the same as if I take modular symbols, rather than doing this bold D, which are these rigid analytic distributions, the dual of power series, I could take locally analytic distributions. And as long as I'm restricting to any finite slope subspace, they're the same. And I haven't explained yet why this is true, and I'm just going to punt on that, and maybe Glenn will explain that in the next lecture. But the reason that this was important is that this theorem has a connection to Pollack L functions, which will be the main topic of the next lecture. But let me just review what's to be said. If I take a modular form and I look at its associated modular symbol here, as long as it's not critical slope, so the slope is less than K plus 1, I can uniquely lift it to an overconvergent Hecke eigensymbol here. And when I evaluate it on this special divisor, 0 minus infinity, what pops out is a distribution, and it is the distribution that is the p-adic L function of the modular form. And that distribution lives here, not here. So that's why it's important to know that, in fact, it doesn't matter which module we used. And the fact that I'm giving these lectures only using this makes things much easier, because this is a Banach space, where this thing is not a Banach space. I forget what it is. It's like a Fréchet space. Is that the word that one uses? It doesn't have one norm. It has a family of norms that determine its topology. So it's much easier to work with Banach spaces. So we do that. But in the end of the day, it doesn't matter because they're the same. Okay, so that's the review. And my aim today is to kind of give, in some sense, 3 proofs of this fact. The first proof will be completely bogus, just to give you some intuition as to how it goes, so just ignoring all convergence issues and several other things. Second proof will be more of a proof, but I'll leave out one detail about how one lifts modular symbols. And the reason I'm going to leave out that detail is that in the third proof, which is Matt Greenberg's argument, it just circumvents that need to lift symbols, and it's a very neat construction, and that's one that's easily implemented on a machine. So that's the plan. So here's a bogus proof 1. I mean proof 1, which is bogus, not all 3 proofs will be bogus. Bogus proof 1. So here's the idea. So to fix ideas throughout the lecture, I'm going to assume that the weight is 0. That means weight 2 on the Reckless mirror, and I'm going to assume that the slope is 0. Meaning I'm only going to be taking ordinary modular symbols here and lifting them to here. But, I'm just going to do it on part of the subspace, but the general ideas are the same. They'll just complicate some of the notation to do it in general. Okay, so let me fix phi, a classical eigensymbol. You know, that's like a phi f coming from some modular form, let's say, with up eigenvalue lambda. And I'm assuming that we're in the slope 0 case, so ordinary, so that means the valuation of lambda is 0. It's a unit. And let phi be any lifting of little phi. This is now some overconvergent modular symbol living here. And note that the point of the theorem is to prove that I can lift it to a Hecke eigensymbol, not just that I can lift it. And I'm not justifying why such a lift even exists. And I will later. That's where Matt Greenberg's argument comes in, to just circumvent any harder arguments. But this is an enormous space. This is an infinite dimensional space, and it's mapping to this tiny little space. So you probably can lift it. I mean, you could lift it, and there's enormous, there's infinite dimensions of ambiguity of how you lift it. So the hard part is not lifting it. The hard part is sort of cutting it down to lifting it uniquely in this small slope space. And just a little bit of terminology. So UP is a compact operator on these space, on overconvergent modular symbols. Or people use the word completely continuous. They're just synonymous things. Which this is a phrase from functional analysis, even if there's nothing p-adic going on. It's just a nice operator, a compact operator. And in particular, compact operators have their eigenvalues tending to 0. So its eigenvalues, lambda 1, lambda 2, lambda n, and some sequence of eigenvalues, and they're tending to 0, so that means their p-adic valuations are tending to infinity with valuation. So I'm not justifying any of this, but don't worry, because there's much less going to be justified in this argument. But the next argument won't need to assume anything about the spectral theory of compact operators. And so if you have one of these compact operators and you have this nice, like, sort of discrete sequence of eigenvalues tending down towards 0, then, well, imagine their corresponding eigenvectors and hope that they're like a basis of the space. And that's what you like, that every vector is some linear combination, infinite linear combination of these eigenvectors. So I'll write the word imagine because that's all I can kind of justify. So imagine, you could write phi as a sum of, let's say phi 1 has eigenvalue lambda 1 and phi 2 has eigenvalue lambda 2, onward. Some infinite sum. And hopefully that the norms of these things are going down, so this is a convergent sequence. We're just saying imagine, so with phi I having eigenvalue lambda I. And the idea, which is standard in these kind of games, is to iterate UP. So I want to start taking this equation and iterating UP. And then the idea would be that these eigenvalues, which have valuation getting larger and larger, when you apply UP, they start getting very, very divisible by P. So they all go away. And then somehow, when you do that enough times, it converges to something. So let me make some more assumptions. Just to make the argument sort of make some sense, let's assume further that, well, I think I want to say that the valuation of lambda I is positive if I is greater than 1. So in this picture here, that the first one I'm not saying anything about, but the rest I'm saying these are all non-ordinary. And it's actually not such a big assumption, because you could pick a phi that makes that happen by using the other Heck operators. You want to go into that and then start iterating UP. So start applying the operator UP divided by lambda again and again. So I'm going to look at 1 over lambda to the n phi acted on by UP to the n for some big capital N. And so when I do that, looking at this equation, well, I'll just do it for each of the terms. So when I hit phi 1 by that, it gets scaled by lambda 1 to the n, and then divided by lambda to the n. And then I get back phi 1, and then that keeps happening for every term. So it's a little n. So then on phi little n, I get a lambda little n to the big N over lambda to the n, onward like that. And the key to this is that this on the left-hand side still lifts phi. And this is how the argument is starting. I'm taking a random lifting of phi, and I want to improve it, and somehow make it in some way getting closer and closer to the right lifting, the Heck eigensymbol lifting. And so I'm going to do that by applying this operator again and again. And UP over lambda, if I thought of that as an operator on classical modular symbols, that fixes little phi, because phi is an eigensymbol with eigenvalue lambda. And so that's why this still lifts phi, and I can write this down. So I want to check that this lifts phi, so let me apply the specialization map to the left-hand side. Well, the specialization map certainly is linear. I can pull out that constant, but it's also Heck equivariant, so I can pull out the UP to the n. So this is the same as specializing phi, but phi was chosen to be a lift of little phi, so I just get back little phi. So that's just 1 over lambda n. Little phi acted on by UP to the n. But little phi is an UP eigenvector with eigenvalue lambda, so then this is just little phi again. So by doing UP over lambda, it changes the symbol as an overconvergent modular symbol, but it doesn't do anything to its specialization. So that's still another lift. And then what do I want to say? Well, I'm assuming that all the eigenvalues past lambda 1 have valuation bigger than 0. I'm also assuming that lambda is a unit. So all of these terms are tending off to 0. The eigenvalues are just making it smaller and smaller. So this is saying that this sequence here, 1 over lambda n phi UP to the n, is converging. Well, what's happening to this term? Ugh. Well, I'll say, this is a bogus argument anyway. What happens is lambda 1 equals lambda, and those cancel, and so this converges to phi 1. Maybe I just leave it there. That's what should happen. That's what should happen. And so, let me just say it in words. There's too much symbols here. I take my phi, the lifting of little phi, and I write out its spectral expansion. And so it's got all these things. One of them is going to be the right one if the theorem is true. So that's going to be my phi 1. And the rest, let's say, all have eigenvalue with valuation positive. As I apply UP over lambda, they all sort of fade off. and it just converges to the right one there. So that's why the theorem is true, at least.
Are you saying that P1 is equal to the original classical P?
Say that again? Phi1 specializes in the classical phi.
Or special, right? Okay.
Yeah, everything that's capital are these overconvergent symbols.
Right.
Yeah. And so that phi1 is supposed to be the thing that's lifting phi, and now is going to be a Hecke eigensymbol because it's one of this, yeah.
A similar bogus proof of Coleman's theorem?
Is there a similar
Bogus proof of Coleman's theorem. Instead of using modular symbols with overconvergent modular symbols.
Yeah. You just do the same thing. I mean, you just take it over and you just pretend that there's an eigenbasis of Hecke. You can do the same exact argument. It doesn't have any modular symbols. So I don't know if you'll hear. The question was, can you make a similar bogus proof of Coleman's theorem on small slope overconvergent modular forms are classical? And one thing to say is you always can make a similar bogus proof just by making it bogus. But I think the exact same argument would work assuming you have this kind of spectral expansion of UP. Okay, so that was proof 1. Let me try and attempt 2 and make this a little bit more rigorous. Let's make this more rigorous. So what steps do we need to do? Well, 1, we need to justify that phi exists. This I already mentioned, meaning that there is at least one lift. And I was saying it's very plausible because the space is infinite dimensional, but how to actually justify this. And the third argument I give will sidestep this issue, but you can do it directly. I mean, you can solve the mounting relations really explicitly. You just do that. And then to lift it, you just have to lift, a modular symbol is uniquely determined by its values on a finite set of divisors. And so you lift from sim k to distributions for all of those in such a way that preserves all the mounting relations. And you just do it really carefully. And you can do that. Okay, so that's it. That's all I'll say about 2. About step 1, you can lift it. So then 2, I don't want to write down this spectral expansion of these phi's, which are eigensymbols, and writing phi as a sum of them. So the key is to look at this sequence, though. That's what ultimately happened, is that this sequence converged to the right answer in this kind of hypothetical argument. So just try and check that directly. So I should look at phi acted on by up to the n over lambda to the n and prove this is Cauchy. Converging to say phi tilde. And this phi tilde will hopefully be the right answer. So that would be the third step, is check that phi tilde is an eigensymbol lifting phi. Right, so these ideas are motivated by this argument, but if you could just check this directly, just look at that sequence and check that it's Cauchy, then you get an overconvergent modular symbol in your hand, and check that it still lifts phi, and check that it's an eigensymbol, and then you're done. In fact, that only checks the surjectivity of the map. I should say something about the injectivity, and so, and even more, so phi tilde is independent of lift. So it doesn't matter what you started with, and that would show the map is actually injective. Okay, so that's the 3-step plan. I'm still going to assume that the ord is 0, but this will still be Cauchy even if the ord is not 0, as long as you're not in the critical slope case. In the critical slope case, this won't be Cauchy, but almost the same arguments, you can check that it will be Cauchy, but it's just a little bit more technical. I mean, you'll be dividing by some non-unit there, but there'll be somehow enough things in the numerator that cancel it out, and it works out. Okay, let me address number 3. Why do you even expect this to work? So, for 3, well, I want to check for you that it lifts phi, and well, that's so note. So why is this true, that phi tilde lifts little phi? Well, this is true since each term in the Cauchy sequence does. Since each phi acted on by up to the n over lambda to the n does. That's the argument I made for you before, that acting by a up over lambda doesn't change the specialization. And so if every single term in the sequence lifts phi, then their limit lifts phi. So that's fine. And why is it an eigensymbol? I want to justify this for you. Well, let's just compute. I take phi tilde and I act on up, and phi tilde is the limit as n goes to infinity of 1 over lambda to the n, phi of up to the n. That's phi tilde, and then I'm acting on up one more time. Okay, so then that's the limit. As n goes to infinity, I have 1 over lambda to the n, phi acted on by up to the n plus 1. So let me pull out a lambda. This is the standard argument. People know, like when you, the fact that you keep iterating by up over lambda is forcing it to become a, for just formal reasons, a eigenvalue lambda. So I pull out a lambda, and I get a limit. Well, now I have 1 over lambda to the n plus 1 of phi acted on by up to the n plus 1. But then this is just phi tilde again. Does that make sense? It's just it's like when you know, this tricks you do with, like, I'm not going to say, it's a standard trick that you do all the time. You just plug something back into itself again and again, and it converges to what it has to converge to. That's just formal. And step 2 is where the content really is. That in fact that the sequence is Cauchy. The thing is, whenever you can get these things to converge, go ahead. I'm not going to justify that rack up. Yeah. I'd say it's in the notes, but it's not. Okay, so then why is this a Cauchy sequence? Well, I guess we'll just, let me turn my page and see. I can just check it directly. Just apply the definition of Cauchy. So I'm going to take an n and then take an m and look at this difference. And to check that that's Cauchy, I have to convince you that that's small. Okay, so let me assume that n is less than or equal to m. And so then I rewrite this. I factor out a 1 over lambda to the n. And I write this as, hope I'm getting this right, phi minus phi stroke up to the m minus n over lambda to the m minus n, and then I gotta put back in the up to the n. Let's see if I did that right. If I act, up to the n is acting on everything, and so, yeah, that looks okay. And then the reason I wrote it this way is look at what's in these parentheses. You have phi, and then you have phi acted on by up to a power over lambda to that same power. So those two things both have the same specialization. They still specialize to phi, which means that their difference specializes to 0. So this is in the kernel of specialization. Since both terms specialize to phi. Okay, and so then the Cauchiness will follow from the following claim. So here's a claim. If I have some modular symbol psi, overconvergent symbol psi, in the kernel of specialization, then when I act psi by 1a0p, this is divisible by p. And so if this is in the kernel specialization, I'm starting, when I act up on it, up is just acting by those matrices 1a, 0p for a running between 0 and p minus 1. So each time I act once, I pick up a p. If I act n times, I pick up p to the n. So then that gets really small. Except this doesn't quite make sense, actually, because we're in a Banach space, so things aren't divisible by p. So I should write that more carefully. So, but there's meaning here. So what do I mean? I mean, I'm starting with something which is norm 1, and then after I apply this, the norm goes down. So now it's p times something in the unit ball. So that's what I mean by divisible by p here. It's p times something in the unit ball. And so let me say it again now that this is stated correctly. If you believe the claim, then this thing's in the kernel specialization, and each time I hit it with up, I'm somehow decreasing the norm by a factor of p. And so I do that n times. This gets really small. That's what I need to show for Cauchy-Mix. Okay, so then why is the claim true? I hope people believe this. So the claim implies that it's Cauchy. So we just have to check the claim. Well, the claim follows from the following subclaim. Just unraveling definitions here. Instead of working with a modular symbol, let me take one of the values of the modular symbol. So let me take mu in D, where mu at 1 is 0. So it has total measure 0. And to say that psi is in the kernel of specialization, that just specialization in the weight 0 case just is total measure. So that's just saying all the values of psi are things like this. They're distributions whose total measure is 0. And so I want to claim that if I have one of these of norm 1, then when I act on these by that matrix, this is divisible by p. Again, meaning that it's p times something in the unit ball. And then I claim that the subclaim implies the claim. But that's just clear because if I want to check that this is true, I take this thing and I plug in a divisor, and the way it acts on the divisor and it acts on the value. So all the values satisfy this property. So then the values become divisible by p. So that's just directly from the definitions. So we just have to check this fact about distributions, that if you have a distribution of total measure 0, that when you act on it by one of these matrices, it becomes divisible by p. So let's just check that. So I take my mu and I act on it. I want to see that this thing is divisible by p. Well, let me plug in something of norm 1. Let me plug in a z to the j, and I want to see what it comes out with is divisible by p. So the definition of the action is you just act on the function. And then if you recall what the definition of the action on a function is, we're in the weight 0 case, so you don't have the orthomorphy factor. And then it was bd. So if you have a, b, c, d, it's b plus dz over a plus cz. And so that becomes a plus pz to the j. And so when I binomial expand this out, I have a bunch of p's, right? Every single term has a p except for the very first term. So this is mu of a to the j plus j choose 1, a to the j minus 1, p of z, there's the p, onward and onward, up to p to the z, to the j. So all of these terms have a p in it, but this one doesn't. But I'm assuming that mu kills 1. So mu kills off this term. So this is the same as mu, that dies, and I get p times something. And that's what I need. So I think that's a proof. Makes sense. These are in the notes. If you want to look through it. And I should still check uniqueness for you. What we check now is that as long as you can, we're assuming that you can lift, you start applying up over lambda, you do that again and again, it converges to something, that something is a up eigensymbol, and then you want to know that, in fact, there was only one up eigensymbol lifting. Well, if you can prove that it was independent of what lift you picked, then you just pick the up eigensymbol, and when you apply up over lambda, that just stabilizes it. So that's what it has to be the answer. So the last thing we should check, step 4, is uniqueness of phi tilde. So just pick 2 lifts. Pick 2 lifts, phi and phi prime. These are lifts of phi, little phi. Well then, phi minus phi prime specializes to 0. It's in the kernel of specialization. And I want to do, if I took phi, I apply UP over lambda to it many times, or phi prime, I apply UP over lambda many times. I want to see they go to the same thing. So it's enough to check that this difference, when I apply UP over lambda to it many times, it goes to 0. But it's in the kernel of specialization. And we just checked through the last claims and subclaims is that when you have things in the kernel of specialization, you apply UP to them, they go to 0. So by the previous claims. Phi minus phi prime, UP to the n, tends to 0. So that's it. Yeah, perfect. So people heard that. You can get the other heck operators from this once you know uniqueness. Because you take TL over AL. TL over AL applied to that. That's going to be another lift. And so it's forced to be this thing again. Exactly. Okay, so that's proof 2. Now on to proof 3. And before doing proof 3, this is Matt Greenberg's argument. Let me just spend a little bit of time discussing how one actually works with distributions on, let's say, like a computer. If you wanted to approximate distributions, how could you do that on a computer? And actually, working this out leads to this nice filtration that Matt used to make a very nice argument of how one can lift symbols. So let's first do the approximation. Okay, so we know that if I take any distribution, then the data of a distribution is the same as the data of its sequence of moments. And so if I give you a sequence of elements in ZP, let's say, how would you approximate them? Well, a naive way to approximate it is take a bunch of them and look at them mod p to some high power. That's an approximation. So fix integers m and n, some big integers, and consider the first n moments of mu each mod p to the n. And that's fine. If you do that over all m and n, then you can completely recover mu. If for every m and every n you know the first m moments mod p to the n, well then just take more and more moments and get more and more accuracy. So that's fine in sort of storing distributions. However, for our purposes, it's completely useless. So unfortunately, this data is not stable under the action of sigma naught. And what do I mean by that? Like if I handed you the shadow of a distribution, meaning its first n moments mod p to the n, and then I asked you, okay, act a matrix on it and tell me that same information, you can't do that. You sort of lose some accuracy. So this data for mu does not determine the same data for mu stroke gamma. And the key problem, so I'll say indeed, if I have some distribution which, let's say, vanishes for the first so many moments for j running between 0 and n, it's not true that mu stroke gamma has the same property. So you imagine you're approximating some distribution like this one whose first n moments vanish. So in your computer, what do you store? You store n zeros. But then you add gamma on it, and well, your computer thinks it must be 0, so it's going to be 0. But in fact, the new distribution has non-zero moments in the first few values. And so that's just a complete nightmare. And I thought I would sort of show some examples of this phenomenon of distributions whose first moments vanish, but then when you act by matrices, those moments come back again. And by looking at this, you actually can see what the fix is to all this, what kind of accuracy you actually have. So let me fix a particular distribution. Let me say mu4 is the distribution that has the following property. If I take mu4 and I plug in z to the j, I either get 1 or I get 0, and I get 1 when j is 4, and I get 0 everywhere else. If I think of the elements z to the j as a basis of A, then this is an element of the dual basis. So it vanishes away from z to the fourth, but it's 1 on z to the fourth. And let me take a matrix gamma to be 1, 0, minus p1, and then I want to consider this new distribution and then look at some of its, and note this one has the property that its first 4 moments vanish. On 1, z squared, and z cubed, it vanishes. So I want to see what properties does this distribution have. So let me first take its total measure. And the action here is mu4, gamma acting on 1. Well, 1 is just the constant function. So I get 1 again, which vanishes. So that one's fine. And actually that's not surprising because the kernel of specialization is stable. So that's just saying mu4 is in the kernel of specialization, so an act by gamma it's still in the kernel of specialization. The problem is when we look at the next moment, if I plug in z, so this is mu4 of gamma on z, so that's mu4 of, so this is the weight 0 action, so b plus dz over a minus pz. Yeah, I think that's right. And so how do I mean, you might look at that and say, wait a second, everything is, you've been telling me it's been lies. You know, this action on A is a power series ring. And that's not a power series, that's a rational function. So why is that even an action? Well, that's actually a power series, right? Because the bottom's a geometric series, so you can expand it out. And you always can do that with these linear fraction transformations, and things remain convergent on the closed disk as long as C is divisible by P. That's that P there. So I can rewrite this as mu4 z times that geometric series, which is just 1 plus pz plus p squared z squared, and so forth. And now, what does mu4 do? It just looks at this power series, and it throws away all of the monomials that are not z to the fourth, and it just picks out the z to the fourth term. So that's z times this, so this is the z cubed term, so this is just p cubed, which is not 0. So that's illustrating one thing. And then let's do another little numerical experiment while we're here. Let me act on by gamma and then plug in z squared. And now it's the same business. I act on z squared, so that's z over 1 minus pz squared, and then I write that as a power series. So that's z squared times the geometric series squared. And then again, I have to pull out the quadratic term. And since there's a z squared there, that's the quadratic term here. And I have to square that power series. And oh, that's not bad. You get a p squared twice, and then another p squared. You get 3p squared. I think that's right. I think that's right. And then you do it again. Let's do one more moment, and just to see what's going on. On z cubed, well, you go ahead and do it, and let me just copy it out of my notes. Oh, I got 3p squared, so that's a good sign. And then 3p. So each of the moments is non-zero, but notice there's this funny pattern that occurs, is that although they're all non-zero, the lowest one is kind of highly divisible by p, and then a little bit less divisible by p, and then a little bit less divisible by p. And if you compute the z to the fourth, there's nothing there. There's no reason that that's going to be divisible by p. What did you say? There was a question?
Is it going to be 1?
Oh, is the answer going to be 1? I don't know. At p is 3, it's a little bit more divisible by, yeah, it's just a little bit more divisible. Yeah, then you're kind of in a little bit better shape, just a little bit. So we can formalize this property. Let me do that. So let me let d0 be the unit ball. I mean, unit ball, concrete thing. It just means that all of the moments are integral. All the moments are in ZP. And then I want to define for you a filtration on this unit ball that's going to mimic this pattern here. So I want to take all the mu's so that the jth moment is divisible by p to the m minus j. And this really only makes sense for j between 0 and m. So what it's saying is that the 0th moment is divisible by p to the m, then the next by p to the m minus 1, then p to the m minus 2. So you ask for less and less divisibility, which is what we saw here. Here the first moment was 0, so it was divisible by p to the 4th, and then p cubed, and then p squared, and then p. So this would be an element of film 4. And so what the basic fact is that this example was supposed to illustrate, in lieu of giving a proof, is that fill m of d0 is stable under sigma naught of p. And that's what this is illustrating, because this mu4 has its first 4 moments vanishing. So of course it satisfies this condition of the first few moments being somewhat divisible by p. They're all 0. And then when I act on it, you can't ask that those moments are still 0, but what you can ask is that they have this exact divisibility pattern. Well, not the exact divisibility pattern because of 3, but at least this much divisibility. And they always do. That pattern always emerges. And so then this gives a way of approximating distributions, because now I can define, let me say, script f of m to be just I take the unit ball and I mod out by this filtration. And what is this as an abelian group? Well, the numerator here, d0, that's just sequences in ZP. So that's just infinitely many copies of ZP. And then the denominator here, you just ask that the first one be in p to the m ZP, and then p to the m minus 1 ZP, and then decreasing down until, again, it's all ZPs. So that infinite tails of ZPs cancels each other out, and you just get an isomorphism of abelian groups of z mod p to the m, z mod p to the m minus 1, down to z mod p. And this has an action of sigma naught, because the unit ball does, and this filtration does. And lastly, so this is what we call this finite approximation module. I should write that down. Finite approximation module. And then note that d0 is isomorphic to the inverse limit of these finite approximation modules. It's just organizing the data in a different way. If I give you a distribution and I know its projection to each of these modules, I'm saying I know the distribution. Well, if I want to figure out the 100th moment, mod p to the millionth, then I look in the million plus 100th filtration. And then the dual milling, I go 100 past them, and then the dual milling down gets me to the exact accuracy that I need. And so I can get any moment arbitrarily well approximated, and so then I get this isomorphism. And this isomorphism for me is the perfect mechanism for representing something on a computer, because this is a finite set, right? Finite. So you can just put that into a machine, and as you increase m, you increase the accuracy, as much as you need to approximate what you're getting after. So this is where we always did our computations with modular symbols. And now I want to use this filtration and go through Mac Greenberg's argument to show how you could use it to make really a theoretical argument to prove that comparison theorem. Okay, so let me reprove the comparison theorem again. Using Mac Greenberg's argument. So first thing I want to do is slightly modify the filtration. Namely, I just want to, let me call it fill tilde of m. I'm going to make it slightly bigger by just intersecting with the kernel of specialization. So this is, when I'm saying reproving this, I'm still in the weight 0, I'm still in the ordinary case. And so the kernel of specialization just means your total measure is 0. So to be in the filtration means that your first moment is at p to the m, and then p to the m minus 1, and onward. And to be here just means your first moment is 0. So just making a slightly a smaller thing. And the reason we're doing that is that kind of mentally, the specialized thing we're going to pretend we know exactly. Like a classical modular symbol values in z, and you know it exactly. And so we don't have to mod out by anything on the 0th moments. We know those exactly. So we intersect with the kernel of specialization here. And I could define sort of f tilde of m. Now this is going to be isomorphic. So by definition, just again d0 mod this modified filtration. And that's a copy of zp for the 0th moment. And then this accuracy thing starts kicking in. Down to zp. And then here's the idea of the proof. Sorry, we have modular symbols, let's say with values in d0, and this is mapping down to modular symbols with values in weight 0, so let me just say values in zp. And d0 is this inverse limit of these things, or even of these things as well. And so I can put in between f tilde m, and I have maps like this. And this is why I intersected with the kernel specialization. This really maps down to everything in ZP. That's the first ZP that's sitting there. And I have living here my classical modular symbol, which is a Hecke eigensymbol, and I want to lift it to here to be a Hecke eigensymbol. And the idea is you just lift it one step at a time. You lift it to F1, then to F2, and then to F3, and you somehow do those incremental steps. And if you could do every single step, then because of the inverse limit statement, well, then you can get it all the way to the top. So we seek sort of partial lifts in here. So we want to build, still on the screen, build phi n, taking values in, I guess I'm calling these m's, phi tilde of m, lifting the next, so where phi m maps to phi m minus 1, and phi m itself is an eigensymbol. And I'll now argue for you inductively that we can get up the whole tower. So assume we have a phi, such a phi n. And then we're going to build the phi n plus 1. Okay, so phi m is a map. It's a homomorphism from delta 0 to phi tilde of m. So I want to lift it, and it's gamma 0 invariant. So you somehow want to do the same trick of lifting it, but that's the point I kept punting on, like how do you lift and still maintain the modeling relations? And so here's the idea, is just lift randomly. Just make a random lift. So pick psi m plus 1, mapping delta 0 to f tilde m plus 1, lifting phi m. This phi f of m is a quotient of f of m plus 1. And so when I say lifting, I just mean as a map. So how do you do this? I mean, one of these things is just a sequence of numbers mod various powers of p, and you want them to be accurate mod one higher power of p. So just randomly pick a number in each of these things. Like, how could that possibly work? I mean, it's not unique. There's nothing. I mean, and like, what properties does this thing have? And in fact, nothing. I mean, this is simply in maps. I mean, by maps, I just mean random set maps to here. But we have to do something, and like in all those other arguments, the key was to use UP. And so here's the magic that makes things work. So if I take phi m plus 1, and I define it to be psi m plus 1 acted on by UP divided by lambda, this is again a map from delta 0 to this finite approximation module, but in fact, phi m is additive. It's gamma 0 invariant. It's independent of lift and satisfies phi m plus 1 acted on by up is lambda times it. And so all the choices that you made in that lift just somehow magically disappeared when you applied up. And that gives a perfect algorithmic way to construct these eigenlifts. You start with your classical modular symbol and you make your random lift, apply up. Make your random lift, apply up. And you just keep doing this until you get your desired degree of accuracy. And I'm going to take maybe just 2 minutes. Am I reading the clock right? I'm over in time. Who am I supposed to be looking at? And I'll take 2 more minutes. I'm just making sure I don't have a half hour, or I've already gone over a half hour. Yeah, okay. So let me just try and say at least a word as to how one might check this. So why the magic? Well, let me check that it's additive. So in order to check that this new thing is additive, I should look at an expression like this. And I want that to be 0. So phi m plus 1 was just psi m plus 1 acted on by this up. So this is 1 over lambda, the sum of all those matrices 1a 0p of psi m. Let me let gamma a be that matrix 1a 0p. So gamma ad plus gamma ad prime minus this whole thing, and then I have to act on that matrix 1a 0p. That's just unraveling the definition of the Heck operator. And this thing here is psi m is this random lift. So it's not a modular symbol, but it is a modular symbol. This should be m plus 1, sorry. But psi m plus 1 is a lift of phi m. So it's a modular symbol mod fill m. So that means that it's additive modulo fill m. So this whole expression here is taking values in fill m of d0. And then just check that 1a 0p kills this. At least up to the power of p that you need to define mod fill m plus 1. And the computation to do that is just like the computations I did with you in that, checking that the sequence when you iterate up is Cauchy. Just write down the matrix actions and you just see it. Okay, and so there's the concrete proof. And next lecture will be by Glenn, and he'll discuss now that we have this lifting theorem, lifting and constructing the periodic L function in both 1 and 2 variables. I'll end there.